everyone. Welcome into lecture number 11 of differential equations. Today's lecture is on second order linear homogeneous equations with constant coefficients, part 2. So we had part 1 in the last, a couple lectures ago, 2 lectures ago. This is part 2 now. So recall that we're going to recall the definition here, that a second order linear homogeneous differential equation with constant coefficients is a differential equation that has the following form. So it's going to be a y double prime plus by prime plus c times y equals 0, where here a, b, and c are real numbers and a is not 0. So there's some leading coefficient here that is not 0. Okay? Again, we talked about this in lecture number 9, this type of equation, and in lecture number 9 we derived a general way to solve these equations. And we said that if we're given one of these second order linear homogeneous constant coefficient equations, then what we can do is we can write down a characteristic equation. So the characteristic equation for this differential equation is ar squared plus br plus c equals 0. And the whole point of this is that if we can solve for r, then the solutions, right? Then these solutions are of the form y equals e to the rt, right? Where r is a solution of this equation. So where r solves the characteristic equation. All right, so again, in lecture number 9, we talked about exactly what to do, how to do this when our solutions were both real and distinct, right? So in lecture 9, we discussed where the case where r, where there's two solutions, right? R is equal to r1 and r2, so two distinct real solutions. And then we said that our general solution of this differential equation up here, of the differential equation, is the following. So this is all kind of review here. But the general solution, it's important review because we're going to pick up right here where we left off. But the general solution would then be y is equal to c1 e to the r1t plus c2 e to the r2t. Okay? So again, these are the general solution. Or this is the general solution of this differential equation. And then we talked about in lecture number 10 how to prove or how to compute or show that these two functions are linearly independent, right? And so that this is the general solution, indeed the general solution of the differential equation. Okay, well, there are two more possibilities for the behavior of these solutions to the characteristic equation now. So let's write this down. We'll do these one at a time, so I'm going to write this out first like this. Two more possibilities. The first one, which will be item number 2 in the lecture, is that it's possible that instead of having two distinct real solutions, we could have two complex solutions. So this is the first case then, right? We could have two complex solutions to the characteristic equation. And I'll write down the form of these in just a second. So two complex solutions to this equation, the characteristic equation, ar squared plus br plus c equals 0. And so these solutions would then be of the form that, remember, they have to come as complex conjugates in this case, right? So it would be lambda plus or minus I times mu. And so the criteria here is that lambda and mu will be real numbers. So those are the real and imaginary part of the complex solutions. And for this to be complex, right, then mu is going to be equal, not equal to 0, right? We want to make sure that it has an imaginary part if this is going to be complex numbers, right? So this is two solutions because one of them is the answer lambda plus I mu, and the other one would be lambda minus I times mu. And the question becomes, how do these roots of the characteristic equation translate into solutions of the differential equation? So remember that this is what we derived in the last lecture, again, lecture 9. So a couple lectures ago, we derived that this was the formula, e to the rt. that's still going to be true down here because this characteristic equation came from plugging in e to the RT into our differential equation and then solving for the values of r that make this the solution, right? So if we find that these complex numbers are the ones that belong in the exponent, then that means this is the solution, right? So the solution in this case is of the form y equals e to the RT again. Remember, that's where this all came from, which in this case will be e to the lambda plus or minus I mu t. So this, I'm writing plus or minus here. This is really two different solutions, right? It's e to the lambda plus I mu times t and e to the lambda minus I mu times t. And when I say times t, I mean the whole thing, right? Parentheses. Okay, so we need to make sense of this. Well, one thing we can do is just apply our exponential rules here, exponent rules, and this can be written as e to the lambda t. That's a real part, so this is okay, right? So this is just an exponential function, and then times plus or minus. Again, this will be two different possibilities here, but I times e to the plus or minus I times mu times t. So here we have our imaginary part, I times mu times t. Remember, t is a real variable, mu is a real number, and so this is e to the I times something, right? Plus or minus something. So this is the part that we want to investigate now. We want to investigate this right here, e to the I times something. So let's recall, and hopefully you guys have seen this in Calculus 2, but recall there's something called Euler's equation. Well, there's actually lots of equations called Euler's equation or Euler's formula. But one version of this is the following. Euler's equation, or again, Euler's formula, sometimes it's called Euler's formula, is given by this, e to the I times theta. So here theta represents any real number. We've got our imaginary I. So for us, the theta is going to be plus or minus mu times t. But in general, it's e to the I theta equals cosine of theta plus I times sine of theta. All right, so this is something that you should have proved when you studied infinite series in Calculus 2. So this can be done by writing the power series expansion for e to the I theta and very carefully separating it out into real part and imaginary part, and noticing then that the remaining power series, the real part of the power series is the cosine, the power series for cosine, and the imaginary part of the series is I, can be factored out, I times the power series for sine of theta. And so this can be proven or derived by using power series. So if you haven't done this, or if you haven't done it in a while, you can derive this formula using the power series. And that'll be good review, because we're going to be studying power series later in this course. So, and it's also just a good illustrative example here, a good exercise to do. So derive this formula using power series expansions. And again, the idea is you start with the power series for e to the I theta, you write out, a bunch of terms, enough that you're going to notice a pattern, and then you break it up into real part and imaginary part, and then investigate those further. Okay, so, but regardless, so if you need to, pause the video here for a moment, work that out, or maybe do it later. But for now, we're gonna just use this formula. We're gonna take this for granted. So for us, what this means then, if we plug in, is that our theta is going to be, we're going to have two options, right? Plus mu t and minus mu t. And remember, mu is not 0, right? So those are going to be different. So what we have then are the following. Our solutions are thus sines and cosines, right? So we'll say, I'm going to name this something different. We'll see why. I'm going to call this phi1 to start with, but e to the lambda t times, and then I'm going to plug into this formula, right? Let's write it in 2 steps. E to the I mu t, positive, and so this one's going to be e to the lambda t times cosine of mu t plus I times sine of mu t. Okay, so there's one solution. The other one is going to be phi2, we'll call it. This one's going to be e to the lambda t times e to the minus I mu t, gets the minus sign. So e to the lambda t, that part's the same. These are going to now, the trig functions are going to be cosine of minus mu t plus I times sine of minus mu t. And then remember that cosine is an even function, so it eats its minus signs, right? So this one, it's symmetric over the y-axis, if you think geometrically of the graph. So this is just going to be cosine of mu t again. Sine is an odd function, and so that minus sign is going to come out. So actually, our phi 2 is e to the lambda t times cosine of mu t minus I times sine of mu t. Okay? And so now, what do we have? Well, our general solution should be a linear combination of these two. Notice that they're built out of the same function. So now you're probably starting to wonder, how is it going to be possible that these are going to be linearly independent? They are. So it turns out that we can write this in a couple different ways. One way to write the solution is to write it as follows. So our general solution y can just be written as follows. So it can be written as C1 phi 1 plus C2 phi 2. So this is C1 e to the lambda t cosine of mu t plus I times sine of mu t plus C2 e to the lambda t, that's showing up everywhere, right? Cosine of mu t minus I times sine of mu t. And then what you could do is you can now multiply these out, and you can, by the way, so in this case here, it's possible that C1 and C2 are actually complex constants. So C1 and C2 are complex in this scenario. And the reason for that is because we need this to be a real solution, right? So we started with a real differential equation. Let me rewrite it right here, right? Our differential equation was ay double prime plus by prime plus cy equals 0. We're expecting to get real solutions to this. A function y as a function of t that lives in the xy plane. That's a real function, or the yt plane in this scenario, right? T is the independent variable. So we're expecting real solutions. And so that means that the constant C1 and C2, they have to interact in such a way that this I, this imaginary I, is going to somehow be canceled out and made into just a real, this will just be a linear combination of the real functions, e to the lambda t cosine of mu t and e to the lambda t sine of mu t. And so, as a recommended exercise again, this can be worked out. So we can solve for new constants, which I'm still going to call C1 and C2 because that's what we usually call them. All right, so C1 and C2 that are real numbers. All right, so these will be real numbers then, or real parameters, you might say, because remember, you don't determine the constants until you have an initial condition, right? But they're going to be real parameters, and such that the general solution is going to be in the following form. And I know this is a lot of kind of circular reasoning in some sense, but it's all going to become clear once we actually do these problems. But the general solution is of the form, so in this case our general solution is going to be y equals C1 e to the lambda t cosine of mu t plus C2 e to the lambda t sine of mu t. Okay, and so in this case, notice the imaginary unit, is not in this solution. So we can solve for our constant so that we have a purely real solution to our differential equation. All right, and so you just work that out by multiplying through, solving a system of equations. You probably want to call them something different. Maybe up here you would call these K1, K2, and then you can solve for C1 and C2 in terms of these constants K1 and K2 from up here. All right? And they'll end up being real, so they have to be real, C1 and C2. All right, so this is the general solution we can just write this down. This is the point. So once we solve our characteristic equation and we get the roots of this form, complex roots, right? So we get these complex roots. They always come as complex conjugates, right? So real plus or minus I times mu, okay? Lambda plus or minus I times mu. Once we have those constants, then we plug those into this formula, lambda and mu, and we're done. So that's all we have to do from now on. So a couple things that I'd like you guys to do. First of all, I'd like you guys to take a minute. This is a recommended exercise, but I'd like you guys to take a minute, pause the video, and do this one right now. Because this solution, right, we need to check and verify that the Wronskian of this is non-zero. So we need to verify that this is indeed, that the e to the lambda t and cosine mu t and e to the lambda t sine of mu t, that those form a fundamental solution set for our differential equation. So verify that the Wronskian of these two, what we'll call like basis solutions, so it's cosine of mu t, e to the lambda t sine of mu t, we need to verify that this is non-zero. All right, so why don't you take a few minutes and work on that, and when you check back, we'll do another example. All right, now that you guys have verified that that Wronskian is non-zero, then we know that this is indeed a fundamental solution set for that differential equation, right? So for the second order linear homogeneous constant coefficient equation where the characteristic roots are complex conjugates, right? Complex conjugate roots. So let's now do an example where we just solve an initial value problem. So for this one, this is item 3 of the lecture, solve the initial value problem, the IVP, with the following data. So let's just do a pretty straightforward one. Y double prime plus y equals 0 with the initial conditions that y of pi over 3 is equal to 2, and then y prime at pi over 3 is equal to negative 4. So again, why don't you take a few minutes, work on this one yourself, and then come back and we can check your answer. Okay, welcome back. Let's see how we did. So the first step to solving an initial value problem is always to find the general solution of our differential equation. In this case, the characteristic equation of this differential equation is going to be r squared plus 1 equals to 0. Remember, derivatives become powers of r, so y double prime becomes r squared when you just translate this into the characteristic polynomial. And then this one can be solved either by factoring or just by noticing that, of course, that means r squared is equal to negative 1, so r is equal to plus or minus I. And I'm going to rewrite this as r is equal to 0 plus or minus 1i. Well, and you don't have to do this every time, but the point here is that now we're going to break this up into our lambda. Lambda is 0, and our mu. Mu is 1, right? So we've got complex solutions. They are complex conjugates of each other. I and minus I are complex conjugates of one another. And so our solution, our general solution, is going to be y equals c1 e to the lambda t cosine of mu t plus c2 e to the lambda t sine of mu t. And now we plug in these values, right? Well, look what happens when we plug in lambda equal to 0. Our solution is going to be e to the 0 times cosine of mu is just 1, right? So cosine of t plus c2 e to the 0 sine of t. And of course, e to the 0 is just 1, right? So our general solution is c1 cosine t plus c2 sine of t. So just a linear combination of sine and cosine. So that's the general solution to this differential equation. And now what we need to do is plug in the initial data, right? So we plug in the initial point. We're also going to need the derivative. So let's take the derivative first, and then we can plug in our initial data. So when we take the derivative of cosine is minus sine, right? So this will be minus c1 sine of t, plus the derivative of sine is positive cosine, so c2 cosine t. All right, and now at this point, we can plug in our initial data. So our initial data was y of pi over 3. On one hand, that's equal to c1 cosine of pi over 3 plus c2 sine of pi over 3. And of course, we know what these values are, right? So cosine of pi over 3 is a half, and sine of pi over 3 is root 3 over 2. So this will be c1 times a half plus c2 times root 3 over 2. And this is supposed to be, by the initial data, equal to 2. All right, we do the same thing for the derivative. Y prime at pi over 3. This one's going to be minus c1 sine at pi over 3. I'm just writing out all the details for this one. Plus c2 cosine pi over 3. And so this one's going to be c1. Here, I'm going to write it in the same fashion here. c1 minus root 3 over 2 plus c2 times a half. And that's supposed to equal negative 4, right? Negative 4. And so to solve for c1 and c2, now what do we have to do? Well, we can just multiply everything by 2 to get rid of the fractions, right? And we can rewrite our system as follows. So we can write this as c1 plus root 3 times c2. That's going to equal 4. Multiply everything by 2. This one's going to be minus root 3 c1 plus c2. Whoops, c sub 2. I'm going to move it though. So plus 1c2, and that's going to equal minus 8, right? And so now we can do this by elimination very easily. So for example, we can multiply this one by negative root 3, the entire equation, and then add these up, right? If I do it, so let's multiply by positive root 3 if I'm going to add them up. So what I meant to do was that, right? Positive root 3 times all this. So what's going to happen? These are going to cancel. So root 3c1 minus root 3c1. This one's going to become 3 plus 1. So that's going to be 4c2. And this is going to be 4 root 3 minus 8. And so this tells us right here then that c2 is equal to root 3 minus 2, just dividing through by 4. So there's our constant. There's our constant c2. Now once we know c2, how do we find c1? We go back to this original equation, right? So c1 is equal to 4 minus root 3 times c2. So that's 4 minus root 3 times root 3 minus 2. So that's going to be 4 minus 3 plus 2 root 3. And that's 2 root 3 plus 1, right? 2 root 3 plus 1. Okay, so those are our two constants, and now we just have to plug these back into our equation. And we can obviously leave these exact with the root 3's in there, but our solution becomes y is equal to c1 cosine, right? So it's going to be 2 root 3 plus 1 times cosine of t plus c2, so that's root 3 minus 2, which is a negative number, but that's fine. Leave it like this, right? Times sine of t. And this is the particular function that solves the initial value problem. So that's with coefficients and all, that's the particular function that solves this initial value problem. Okay? All right, so let's now take a look at the next case, the next possibility here of what our roots could be. So now we've talked about, if we scroll back up, in lecture 9, we talked about what we do when we have two distinct real roots. The solution you just plug right in, right? You just plug in as exponents on the exponential, so e to the r1t and e to the r2t. And we checked in lecture 10 that those two functions are linearly independent. So Wronskian non-zero. In today's lecture, we've just worked through the case when characteristic roots are complex conjugates. So that's case 2. And then case 3 is going to be, so this is item number 4 of the lecture, but the last possibility, right? So case 3 is going to be the characteristic equation has a real repeated root. So in this case, it's going to have a real but repeated root, a single root, right? And so in other words, our characteristic equation, a y double prime plus b y prime plus c y equals 0. This is our differential equation, right? This has characteristic equation of the form, after some rewriting, right, as a times r minus r1 quantity squared equals 0. So it can be written as a perfect square. So then the solution is just r equals r1, and this is a repeated root, right? Repeated root. So we only got one answer, in other words, right? But remember, with these second order equations, we learned in lecture 10 that we should be looking for two linearly independent basis solutions that can be combined as a linear combination, right, to give the general solution. So we know then what? We know then this function, right, y equals e to the r1t is a solution. All right, but it's only one solution. So what about the other solution? That's the new question, right? So what about another linearly independent solution? Can we find one? This is the question. All right, and so here's the idea. So the method that we're going to use here, I'll write this later, but we're going to use the method of reduction of order. So we have one solution, and we are going to try to reduce our given differential equation to another one. All right, so here's the idea. Reduction of order. We are going to assume a couple of things here, right? So a y double prime plus by prime plus c y equals 0. All right, and then we're going to assume that this has solution. Just for the sake of writing, I'm going to make it y equals e to the rt. And furthermore, that this r is the only solution of the characteristic equation, right? So this means, I'll write this as and here, the way I'm writing out the hypotheses. But this means the following, right? So a times y, so the characteristic equation, right? ar squared plus br plus c equals 0. This has a single repeated root. All right, so let's think about what the form of this r must be if this is going to have a single repeated root. Well, we know that the quadratic equation, we can find the solution by plugging into the quadratic formula, right? So the quadratic formula says that the solution r is going to be negative b plus or minus square root b squared minus 4ac all over 2a, right? So just purely analytical. This has got to be the solution. But if we have only one solution, that means that this discriminant is equal to 0, right? So it's actually gone. And so this means then that the root r itself must be negative b over 2a. All right? And so you can think about this geometrically as well if you think about parabolas and the vertex of the parabola, etc. There's many different ways to come to this conclusion, but this is one of our, this is a conclusion though that we can draw, right? That r must be negative b over 2a for this equation. All right, so not only do we know y equals e to the rt, but we know that the r is equal to negative b over 2a in this scenario. All right, so here's what we're going to do. Let's suppose or assume the solution, the general solution, is of the form of the following here. So y is a function of t, right? So let's assume that our solution y of t is going to be equal to some unknown function v of t times our given solution, so times e to the rt. So we're assuming now that our solution to the differential equation, to the general solution, is going to be a constant times e to the rt, and then we're going to allow that constant to be a function, right? We're going to allow it to vary. So let's see what happens now. We need to take the derivatives of this and plug in. So y prime of t is going to be, we need to take the derivatives carefully and make sure that we're applying the product rule here, right? So let's start by just doing the following. So let's start by taking the derivative of this one first, actually. So let's write this as v of t times r e to the rt plus, and then the derivative of the in the other direction is going to be v prime of t times e to the rt, right? And now the second derivative, y double prime of t, we need to do the same thing, right? So this is going to be v of t times r squared e to the rt plus, we're going to take a derivative of this and leave this alone. So v prime of t r e to the rt. But then we're going to do it to this one as well, and look at, we're going to get another copy of this, right? So put a 2 there, because the derivative of this, leave this alone, is just the same copy of this. And then plus derivative of this, which is v double prime of t e to the rt. All right, and let's plug this into our differential equation now. So remember, our differential equation is a y prime plus by, a y double prime plus by prime plus cy. And we know that that equals 0, right? So plugging in to the original differential equation, we have 0 on one hand is equal to a y double prime plus b y prime plus c times y. And let's just write this all out, right? So it's going to be a times this bottom one. So a times, I'm just going to write v here and drop the of t just for the sake of writing here. So v times r squared e to the rt plus, this one's going to be 2v prime r e to the rt plus v double prime e to the rt. And then the next one's going to be plus b times v times r times e to the rt plus v prime e to the rt. And then finally plus c times v e to the rt. You can probably fit that on the same line. Barely. Okay, now what we want to do is rearrange this and group this, because we'll notice, okay, that a few of these just have v's, and then let's group it by derivatives of v, basically, is what I'm trying to say here. So when we regroup this now, we're going to have v times, what's the v times? Well, on one hand, it's a r squared e to the rt plus, this one's going to be br e to the rt, right? And this one's going to be plus c e to the rt. And then we have the v prime, right? So this one's going to be plus 2a, whoops, I want to factor this v prime out. So the v prime coefficients are going to be 2a r e to the rt, and then plus b e to the rt, right? Plus b e to the rt. And then finally, what do we have? We have a times v prime. So the v prime term, again, v double prime term, that's the next one, right? Is times a e to the rt. Now, something else I could have and probably should have done here, right, is, and I'll do it now, is factor out the e to the rt from every single term here. It's on this e to the rt is on every single term, right? It's on every single term. And so let's factor that out now. So e to the rt, remember this has got to equal 0, and e to the rt can never equal 0. So here we have our v times, look what's left here, ar squared plus br plus c. Then we have our v prime times, look what's left here, 2 times a times r plus b. Then we have our a times our v double prime. That's all that's left. But again, let's remember where these numbers came from. This one, ar squared plus br plus c, that one is 0, right? Because of the choice of r that we have. That one's 0 because of our choice of r. So this one's gone, right? This one is going to be equal to 0. It's gone. Just cross it off. All right, what about the next one? Well, this one, 2ar plus b. Well, for that one, we can use the other form of our r. We know that r is equal to negative b over 2a, right? So let's plug in. Let's see what happens here. This one's going to be, actually, right? This one's going to be 2 times a times r, but r was negative b over 2a plus b, and I think we're going to see what happens, right? 2a's cancel. This is negative b plus b, so this one's also 0, so that one's also gone. All right, that's also gone. And what we're left with now is just this term. So v double prime times a has to equal 0, all right, times e to the rt, but e to the rt can never be 0, so let's write this out. So now we've reduced this, right? E to the rt is not 0, and similarly, a is not 0, right? That was assumed up here. A is not 0. It's assumed at the very beginning of this whole lecture, right? That a can't be 0 for this to be a second order equation, so a is not 0. And so what that means then, right, then v double prime must be 0. All right? And so how do we solve for v if we know v double prime is 0? Well, we just integrate twice, right? So this one tells us a couple things. So v is equal to what? Just a constant, right? Let's call it c2. And then, whoops, v prime is equal to c2. Integrate once, you get a constant. And once again, v, integrate again. Now what do we have? We have c2 times t plus c1. All right? So this is, after all that work, this is the function v. It's a function v, which when multiplied by e to the rt gives us the general solution of our differential equation. Right? So we just found a formula for this. What does it mean? Well, our general solution must be c2 times t plus c1 times e to the rt. Right? Multiply it out. I'll write it down here. Multiplying it out. So the general solution when there are repeated roots. General solution to this differential equation, ay double prime plus by prime plus cy equals 0 when the characteristic equation, has a single real root, is of the form, so the solution is of the form y equals, scroll back up for one more moment, multiply this out, right? So it's going to be c1 e to the rt plus c2 times t e to the rt. All right, so here's the two parts. c1 e to the rt, that's the one that comes from the root itself. So the root here is r. The real root here is r, right? Plus the second part of the general solution is t e to the rt. So c2 t e to the rt. All right, so that is the solution of the second order linear homogeneous constant coefficient equation when the characteristic equation has a single real root. Then you have e to the rt, that comes from the root, and then to get your second part of the solution, you have to multiply by t, so t e to the rt. And we derive that using this method of reduction of order. So what is the method of reduction of order? Basically, it is this whole process where we said, all right, we know we have a solution, right? We're given a solution. So given one solution, what do? Well, we assume that the form of the second solution is some unknown function times the first solution. And then we took the derivatives, we plugged in, we carefully reduced the equation, right? So this one will always be 0, you'll find. This one will not always be 0. So this was special to this equation, that the coefficient on v prime was 0. In general, you're going to have to solve for a differential equation and integrate a couple of times. So a first order equation, and then you get you have a second order equation, but you can reduce it to a first order equation and then solve two first order equations. All right, but anyway, this is the solution then of the case when we have a repeated root. So just like we did last time, we need to make sure, so take a moment here, to make sure that these two solutions are actually linearly independent, right? So you need to compute the Wronskian. I want you guys to take a moment and do this actually, but show that the Wronskian of these two functions, e to the rt and t e to the rt, that this Wronskian is non-zero. All right, and so actually it's okay if r is 0 in this one. You can do it just for any r. You'll find it. You'll see that when you work it out, but show that this Wronskian is non-zero. So take a moment, work that out, and when you come back, we'll do another example. All right, guys, I hope that went all right. Let's try another example here, or an example with actual functions here, an actual differential equation. So let's solve the initial value problem now. The initial value problem given as follows. So the differential equation is going to be y double prime minus 6 times y prime plus 9 equals 0, 9y equals 0. And the initial values are y of 0 is equal to 0, and y prime at 0 is equal to 2. Okay, so take a moment, try to solve this one, and when you come back, we'll finish it off together. All right, let's see how this one goes. So first of all, again, the first job of solving an initial value problem is always to solve the differential equation. So let's start by writing the characteristic equation for this one. And that's going to be r squared minus 6r plus 9 equals 0. This, of course, factors, and it is indeed a perfect square, right? So r minus 3 quantity squared. And that means that this has a single real root, r equal to 3, which is repeated, multiplicity 2, right? So this fits exactly in the scenario that we have been talking about. So because we did all this work up here, we don't have to redo it, right? We don't have to redo that reduction of order method. We can just plug into this general solution now, and we can say, all right, our general solution is going to be y is equal to c1 e to the 3t, there's one solution, plus c2 times t e to the 3t. There's the second solution. So that's our general solution. Now we have to plug in our initial data. And just like we did in the previous example, we should first take the derivative and then plug in the initial points, right? So let's start by taking a derivative here. The first derivative, and the only one we have to take, right? We only need one derivative. But the derivative is going to be 3c1 e to the 3t plus, and then this one's going to be c2 e to the 3t plus 3t, right? So c2 times 3t e to the 3t by the product rule. And now we want to plug in our initial conditions, right? So y of 0, on one hand, it's equal to 0. And on the other hand, it's going to be c1 plus 0 c2, right? So c1 plus c2 times 0. So it's gone. It's just c1. So right now we know that c1 is 0. All right? That's part of our solution. So actually, it's gone from here, right? So when we plug in y prime of 0, on one hand it's 2, and on the other hand, this part is 0. We plug into here, right? So we get c2 plus, again, 0 here. 0 c2. So this tells us then c2 is equal to 2, and this one is a little more straightforward than our previous one, right? So our general solution is just y of t is equal to 2t e to the 3t. That's the solution to this initial value problem. Okay. All right, there's one more thing that we'd like to discuss in this lecture, and that is Euler equations. So we've seen these before, but let's take another look at them here. So Euler equations are of the form, again, we talked about Euler earlier, and I said this is completely different. I said there's lots of things that are named after Euler, and here's another thing. So this is very different than the Euler's formula that we were talking about earlier in this lecture. But Euler equations are of the following form. So they look like this. They're a t squared. They are second order linear homogeneous but not constant coefficient. All right, so they're a t squared y double prime plus b times t y prime plus c times y equal to 0. Couple things here. Obviously, a, b, and c are going to be real numbers with a not equal to 0 because that would zero out the leading coefficient. And in general, t can't be 0 in these equations either, right? So t is a variable. So usually we'll say you'll be given this information when you solve the problem. So t is greater than 0 or it's less than 0. All right, so let's look at these a little closer. So one thing that we can do is we can make a guess of the solution, very similar to how we did this for the constant coefficient equations. But we can guess that our solution is going to be of the form y equals t to the power r. Okay. Then take the derivatives and plug in. So it's very similar to what we did before. So the first derivative is going to be rt to the r minus 1. The second derivative is going to be r times r minus 1 t to the r minus 2. And then if we plug these into our equation, we now have a times t squared times r minus 1 times t to the r minus 2 plus b times t times r times t to the r minus 1 plus c times t to the r, and that's supposed to equal 0. And now we notice that as we look at these, t squared times t to the r minus 2, that combines to just be t to the r. And same thing with the middle term, t to the r minus 1, those combine to just be t to the r. Here we have t to the r. Again, we're assuming that either r is positive or negative. Let's just assume t is positive here, right? So t is positive. Then look what we have. We can factor out that t to the r, and we're left with this following equation, or this following portion of an equation, a times r minus 1 plus b times r plus c. This whole thing has to equal 0, right? But this one, t to the r can't be 0, right? Especially if t is positive, t to the r cannot be 0. So this portion is what's got to equal 0. So this becomes our characteristic equation for an Euler equation. All right, so for Euler equations, the characteristic equation is a little bit different than it was up above. So let's look. This is going to be ar squared plus, this is going to be b minus a. So if you multiply this out, this is r squared minus r, right? So ar squared minus ar plus br. So this becomes b minus a times r plus c equals 0. And this is the characteristic equation now for an Euler equation, which is given of this form. All right? So this can have real roots. So let's suppose if r is just equal to r1 and r2, if this has two real roots, then the solution is going to be, so let's write this over here actually, case 1. All right? We'll just go through all the same options that we did in our setup with our constant coefficients. But if this is two distinct real roots, right, real roots that are distinct, then the general solution is just going to be y equals c1 t to the r1 plus c2 t to the r2. All right, that's it. A linear combination of those two. So you should check, by the way, that t to the r1 and t to the r2. So this is an implicit exercise that I'm making explicit, right? T to the r1 and t to the r2. This Wronskian should be non-zero if r1 does not equal r2. So make sure you check that. Okay. All right. Case 2 then. Let's look at case 2. Well, what's case 2? Case 2 was, if we go by the order that we went for these constant coefficient equations, would be that r is equal to lambda plus or minus I times mu. So complex solutions, right? Two complex solutions. Well, how are we going to make sense of this? Let's first, for this one, let's notice that if y is equal to t to the r, just forget about this form for a minute, but if y is equal to t to the r, then we can write this as e to the ln of t to the r by the inverse properties, right, of the natural log and the exponential e. And so this can then be written as e to the r ln of t. Okay, and if we plug in our values for r, this is now going to be, so for this value, right, look what it's going to be. It's going to be e to the lambda ln of t times e to the plus or minus I mu natural log of t. This first term, that's just t to the lambda. That's t to the lambda. This one is our e to the I theta, right? E to the I theta. So this whole term, based on what we did with our Euler's method, we can say, all right, there's our theta. That all goes inside of the cosine and the sine, right? So this one's going to be cosine of mu natural log t plus or minus sine of mu natural log t. All right, and so this gives us our general solution in the case of a complex root to our characteristic equation, as y is going to be equal to c1 t to the lambda cosine of mu natural log t plus c2 t to the lambda sine of mu natural log t. All right, and of course, all of these equations really do rely on the fact that this is positive and not negative, right? That t is positive for these log equations here especially, right? Okay, so this is the general solution. I'm just working out the solutions for you, and then, you know, as we can see, once you have the solutions, you just solve a quadratic equation, right? Anyone can do that. Solve a quadratic equation and then plug into the correct form. So the key is to recognize the form of the roots, the characteristic roots, and then just plug into the proper equation, right? So case 3 is that we have only one root, right? So r is just equal to, let's say, r1 repeated, right? Well, we can do the same thing that we did before, which is we can say, all right, by before I mean right here, right? So again, we've got y is equal to t to the r1, which is e to the ln t to the r1, or we could say e to the r1 ln of t. All right, and if you work out the reduction of order formula, you will find that the second solution has to be this natural log of t coming down. All right, so it's got to be natural log of t times e to the r1 natural log of t. Basically, you make a change of variables where you say, all right, you do something like let u equal ln of t, and then you very carefully work out all the details, okay? So I'm going to leave that as a recommended exercise. But after you do it, what you'll end up with is the following. So your y is going to be equal to original solution, c1 t to the r1 plus c2. That's the same as this, right? It's just another way to write this. c2 is going to be that same solution, this term, times a copy of ln of t, right? So it's going to end up being c2 times ln of t times t to the r1. All right, and so those are your two solutions. And again, you can check that those are linearly independent by computing their Wronskian. All right, so this is a recommended exercise to verify, especially on this one, that the reduction of order gives you the second solution of ln of t times t to the r1. Okay. All right, I'm going to leave this lecture here, and I'll talk to you guys in the next one.